Okay, welcome everyone to this talk that I gave. So I gave it live at one point in my life, but it's like really difficult to record. It's better to be here in my warm, nice studio type thing, and so I just decided to record the talk. Right? It's like much better, quality is much better. Problem is, of course, there will be no live interactions. Right? It's a recorded video. My apologies. But anyway, so my talk today is about whether all knots are actually equal, and here is my little picture of exponential decay, and we come back to that later. So I'm going to talk about the quantum knot invariants. If you don't know what these are, doesn't really matter. So we'll see what these are. And I gave this talk in July 2025, right? So now let's see actually what's going on. So I start with a little bit of the history. So even if you don't care about quantum knot invariants, maybe this part of history is interesting. So I will tell you a little bit about how bad actually the homology is, if you want. So yes, Poincaré wrote this sequence of papers called Analysis topology, the old word for topology, Poincaré's word for topology, if you want. This one here was one of the versions from November 1903, so quite a while ago. As I said, I recorded this or gave this talk in July 2025, so let's say it's 125 years ago. Yeah, as you can see already, I can't really compute. But okay, fine, that's just what it is. And there's a famous question Poincaré asked here. I will not translate it. It's a question, and essentially this is a famous Poincaré conjecture formulated as a question. So very often in mathematics, people just want to prove a conjecture of someone, but maybe it actually was never a conjecture to begin with. So the question Poincaré asks is, the only close simply connected three-manifold is a sphere, right? So this was well known for surfaces for a long time, because you can classify surfaces. Yeah, they're donut-type shapes. And for three manifolds, well, classification is quite difficult, or probably very difficult. That's what Poincaré thought at that point. Was right, so it's not so easy. But maybe we can actually kind of answer this question about identifying a sphere, right? So the essentially what this question or this conjecture is all about is everything that looks like a sphere is actually really a sphere. That's what the conjecture is all about. That's not what I wanted, but anyway, we can just scroll on. And the whole problem here is that three manifolds are like really difficult to imagine, right? So if you think about a two manifold, a surface, that you usually need three-dimensional space to imagine it, right? A soccer ball, you need a three-dimensional space to imagine the soccer ball, but the surface of the soccer ball is just two-dimensional itself. So to just imagine a three-dimensional space, you actually need 4 dimensions, which makes them a little bit difficult, right? So I show you a great way to think about them as we go along in this video. But yeah, I hope you get the point. It's like really difficult to imagine them. And yeah, Poincaré was difficult, maybe yes, maybe no. The answer to Poincaré's question is actually yes. But it took a very long time to figure that out. It's this famous theorem, nowadays mostly contributed to Perelman, but there was a lot of work before. Yeah, and it's very difficult. So manifolds are really difficult type of objects as soon as you leave the realm of surfaces. And that's kind of the point here. So we're not talking about arbitrary topological spaces. They're just insane, right? You have no way to say anything about them. So manifold should be kind of the nicest possible topological space, and even they get pretty nasty in 3 or 4 or higher dimensions. Yeah? So that's essentially what it is. And the history of this theorem, Poincaré's question, Poincaré theorem, whatever you want to call it, Perelman theorem, whatever you want to call it, is that Poincaré was trying a lot. And this is kind of where my story starts. Poincaré was trying a lot, developing what is nowadays called algebraic topology, like fundamental group, homology, and all that stuff. And Poincaré's first conjecture was actually that homology detects the sphere, right? So homology detects the three-sphere. Turns out that this is like, yeah, we'll see. So the starting point of my whole paper here, my whole investigation is that this is like as wrong as it could be. It's so wrong, it's almost scary how wrong this is. And kind of has a very, very wrong, it's not really wrong, but it's kind of, people tell you this story in a very strange way, because in algebraic topology you always get the feeling homology is like so good, it's extremely good, but it's really just because people show you homology on easy examples, right? So of course, on easy examples are easy, right? That's the whole point. That's the whole point of being an easy example. So they're easy to distinguish. And yeah, homology will do a good job because everything will do a good job, right? It's not difficult to distinguish a sphere from a donut. Homology can do that. Everyone can do that. So if you can't distinguish an orange from a donut, there is some problem on your end, right? It's a you problem. And homology can do that for you, but it's actually not very exciting. Poincaré was convinced that homology is also good for higher dimensional manifolds, well, at least in the sense of it detects the three-sphere, the three-dimensional soccer ball, but no, it doesn't. Poincaré found a counterexample 1 year after kind of thinking about homology detects the sphere, and I have a better way to generate counterexamples in a second, but essentially how Poincaré did this, so here's a picture from Poincaré's paper, is you take a dodecahedron and you identify the opposite sides. That gives you a closed three-manifold, yeah, but very hard to imagine one. But this three-manifold is not the sphere, but it has a homology of the sphere. It already tells you that three-manifolds, I mean, gluing opposite sides of a dodecahedron, who would do that? But anyway, so it already tells you that three-manifolds are like quite difficult, right? They're not as your orange or your donut, which are easy to distinguish. They're much more subtle. So homology can't detect this funny three-manifold where you glue the opposite ends of the dodecahedron together. Okay, so that was kind of the state of the arts. Poincaré, like the beginnings of algebraic topology, right? So say it again. Poincaré developed algebraic topology essentially to answer this type of question, but all the tools from algebraic topology are not good enough to answer that question. And here's some of the reason why, right? So there's a knot, here's a knot. A knot is really just a closed string in 3 space here, and people usually study it by looking at kind of their shadow projections onto the plane. So here's my little knot, and there are various different shadows describing the same type of knot. Here's another knot, one of my favorite pictures that I stole. I've actually forgot what type of paper it was. I stole it from a biology paper. So this is a knotted protein, and as you can see, biologists do exactly the same as mathematicians do, right? So and it's really kind of a nice story. So knots are the basic building blocks of many different things in real life. So here's one of my favorite pictures. So here you can see the top row is an electron microscope picture of DNA. And DNA knots itself. It's a long string. Long strings get knotted. Just look around. If you're watching this on your home computer right now, and you have cables, they knot themselves. DNA does the same. So second row, somebody has drawn it out, and then third row identified the corresponding knot. Yeah. So knots are literally everywhere. And knot theory kind of started. Knots are the building blocks of low-dimensional manifolds, starting from 3 onwards. For surfaces, you don't need knots. It's kind of the first non-trivial thing. Difference between surfaces and higher dimensional manifolds are knots. Kind of the first non-trivial thing that you see. And people were starting knot theory from, let's say, 1900. Of course, knots were around for a long, long time. But let's say they started in 1900, right? In mathematics in the earliest 20th century. And yeah, essentially what you want is an invariant, so some numerical data like homology or something that you can associate to a knot, and it will help you to distinguish knots apart. But the problem was that all the invariants people studied for a long time, they came from algebraic topology. Yeah, so this is the only tool we had for a long time. Homology in France, algebraic topology, and they're just not good. They're just not good for knots. They're just really, really bad. And yeah, so there was not much progress in some sense in the realm of knot theory. And a lot of questions in knot theory, so I let you guess for a second, are actually pretty difficult. So here's the main problem, right? So here's a picture of a knot. I let you guess what knot it is. Let's go back here. So a knot, the problem is you usually only see a shadow of the knot, and the shadow might vary drastically, right? So very drastic variation of the shadow, but the knot could still be the same. So here's just a shadow of a knot, and it's just a very nasty shadow of a knot, because actually the knot here is the unknot, and here is kind of the illustration why this is the unknot. So there's a non-trivial sequence of moves until it's untwisted, but it is actually untwisted. So detecting knots is like a difficult problem. And all the standard invariants from algebraic topology, homology, and friends, they're just really bad for knots. They're just really bad in general, but we're not quite there yet. But they're really bad for knots in particular. There's just people were unable to do essentially people were unable to do anything with knots. Okay, so these are knots. Very difficult. Knot theory, always fun. Always looks very easy. You can just draw your picture. Everyone knows what a knot is. So yeah, your shoelaces form a knot. But they're actually pretty difficult. And they form the building blocks of low-dimensional manifolds. And I will now explain how this works. So imagine that you have your knot, and the knot is like this little thing. It's really, if you make the knot a little bit thicker, it's really like a rope-type structure, and it forms a torus, actually. It forms a torus. The torus sits somewhere knotted in space. Yeah. And the thing is, you take the knot complement, which is literally the torus sits somewhere in space. You take it out, so take out the knot. You have now empty space that you can fill with cream. This is called the knot complement, and then you take it out and you glue it back in. Of course, if you do that, you have done nothing. But if you take it out and you glue it back in twisted, then something might change, right? So take it out and you glue it back in twisted. So in case it doesn't make any sense to you, it's kind of a little bit difficult to imagine. It's called a knot complement, what I'm doing. So the thing without the knot is called the knot complement. So here's a knot complement cake. A knot complement cake. So people love this stuff a lot. So they bake cakes. So here, where you can fill in the cream, is where you have taken out the knot. I hope that makes some sense, right? The knot sits somewhere in space. You take it out. You have now a hole in space where you can fill in cream. And you have a cake, right? The space here is the rest of the cake, and where the knot is where the cream is. So that makes hopefully some sense in some universe. And I hope you like cake. Anyway, cake. Who doesn't like cake? Cake is great. Cake is actually very nasty. Cake is very unhealthy. But God, this is not a video about being unhealthy or not. Anyway, so the idea is take it out, glue it back in. Of course, you have done nothing, so take it out, glue it back in, twist it, and what happens, right? Any such gluing is determined by, I have a nice picture in a second, by the image of the meridian of the torus and where it goes. So here's my little torus, and you should imagine that this little torus here is now sitting somewhere knotted in space, right? It's just an easy picture of my knot. So every twisted gluing is determined by where you put the meridian of the original torus. And the meridian of the original torus, you glue it to some curve gamma. Here's a blue one, right? You glue it to some curve. And gamma itself is determined by the fundamental clauses, so how often it goes around M and L, the longitude and the meridian. So in this case, it goes around M 1, 2, 3 times, and it goes around L once, right? So you just express gamma in terms of M and L and collect the two numbers, P and Q. And any such gluing, right, any type of this cake gluing, take out the cream, put it back in the cream, is determined by this type of process, right? So how often it winds around. Excellent. really beautiful. So take out, and you just need to remember two numbers. That's what it is. You just need to remember two numbers. And the big theorem in low-dimensional topology, and I only really stated for 3 manifolds, there's an analog statement for 4 manifolds. So lots are really the basic building blocks of, well, 3 or 4 dimensional manifolds. So every 3-dimensional manifold can be obtained by this process, and it's usually called Dehn surgery. It's due to Max Dehn, who was a little bit after Poincaré, so 1908. That's what you should have in mind, right? So pick a finite collection of knots, pick surgery coefficients for each notch, and perform the remove and insert strategy, right? So perform our little cake cream strategy, if you want. So every manifold arises in this way. Every 3-dimensional manifold arises in this way. So knots are really the building blocks of those manifolds. And yeah, so this is probably kind of a good way to imagine a 3-manifold. It's just a knot with a number. And the number, or you could just, actually, the surgery coefficient only depends on the ratio between the two. So the surgery itself. So it's really just a number that you associate to a knot, which is like P over Q, right? The rational number P over Q. So a 3-manifold is a knot, or a link in general, and a bunch of surgery coefficients. And yeah, homology is really bad, because every surgery on a knot gluing meridian to longitude. Pick your favorite knot and just glue meridian to longitude. That gives you an homology sphere. So there are infinitely many homology spheres. There's also a criterion where you can read off how different are those spheres. They're essentially all different. Okay. Every such surgery, gluing meridian to longitude and an arbitrary knot, gives you an homology sphere. The homology sphere is a non-trivial 3-manifold, so non-sphere, with the same homology as a sphere. And that's just really bad. So, right? So there are infinitely many 3-manifolds with the same homology as a sphere. So yeah, this lie, it's maybe not a lie, but it's kind of this slight misinformation that you get in algebraic topology, that homology is the best thing ever. Homology is actually pretty bad. It's disgustingly bad. Yeah? We're talking about the easiest type of thing you can imagine, beyond surfaces, 3-dimensional manifolds, and homology is like extremely bad, even in recognizing a sphere. No? So that's why you have a Poincaré conjecture. If homology would be a good invariant, there wouldn't be a Poincaré conjecture. Poincaré would have solved everything already. No, homology is a really, really bad invariant. Yeah, it's kind of the wrong the lie, I don't know what to call it, but you somehow get the wrong impression, because in algebraic topology, you always learn it on easy spaces. Yeah? Homology can distinguish a sphere from 512-dimensional projective space. But everything can distinguish a sphere from 512-dimensional projective space. These are wildly different objects. You somehow, there is this bias in my head, or at least for a long time there was this bias in my head, that I thought homology was good because I only ever saw it on easy examples. Yeah? So if you look to easy examples, of course it will be good, because everything will be good on easy examples. But actually, in reality, it's not all that great, right? It's a little bit of a nasty thing. Yeah, so to me this came as a shock, but of course this is well known. That was the whole reason why there's a Poincaré conjecture. But somehow the way it's taught is not wrong. I'm still struggling to find a good word here, but it's somehow misleading, if you want. Misleading might be a nice word. So homology is pretty bad. Cool. Anyway, and then there was one of my favorite pictures here. Vaughan Jones, very happy at the Congress of Mathematicians in 1990, taking away the Fields Medal. Yeah, looks very happy. Vaughan Jones here looks very happy. This is Fadeev, by the way, in the background. Vaughan Jones, very happy, takes away the Fields Medal. And here's a quote. And note that the quote never says, so Jones discovered essentially what is called the Jones polynomial, or the quantum invariants, which are not invariants like the Jones polynomial. And I had the same impression as homology. I thought that they were really, really fantastic, right? kind of the same impression, because you always ever see them on easy knots. You ever see them in action on easy knots. Same as with homology. You see that homology can distinguish an orange from a donut, but in reality, what can't distinguish an orange from a donut, and whatever. The Jones polynomial can distinguish the unknot from a trefoil or something, but in reality, what cannot distinguish the unknot from a trefoil? Anyway, but not at the quote. The quote actually says something different. So I should have known better, right? I should have known better. The quote says the Jones gets the Fields medal because whatever you discovered is actually related to many fields, which is very different than saying, oh, because it's a very good invariant, right? It's just related to many things, which is really the seller for the quantum invariants in general. They're related to many things. It's also the selling point for homology. This is related to many things. It's not a good invariant. Homology is not a good invariant. Quantum invariants are not a good invariant. That's just what it is. You just somehow, it never struck me until it struck me. That sounds like a tautology. You know what I'm trying to say, right? So there was this whole story. Jones discovered an invariant called the quantum invariant, Jones polynomial, and that's nowadays a whole zoo of them. Yeah? There's a whole zoo of them, and they're interesting because they're related to many things. So eventually I needed to ask this question, how good are they actually as invariants, right? This is not taking into account how good they are kind of as playing around. They're related to many fields, right? They're interesting. I'm not asking how interesting they are. I'm asking how good they are as invariants. Yeah? You don't actually really need to know what they are. You just need to know that they're invariants obtained from a certain procedure coming from representation theory, essentially. Yeah? So how good are these invariants? It's kind of the question I was asking. I will explain briefly how this works, and you will see that there's a whole zoo of them. Essentially, it works as follows. Take any Lie algebra and any representation of it, and you get one of these invariants, right? So whole family, any Lie algebra, SL15, any representation of it, I have no idea of the 15-dimensional representation of SL15, something like that. And you get one of these invariants by playing the following game. You just bring your knot into this nice little form, where every step is one of the basic operations of a crossing, a cup and a cap. And each one of them corresponds to a map between representations. The R is usually called, the crossing is usually called the R matrix. And the other ones are like pairing and co-pairing operations. And you just compose all of these maps, and you get a nice number. And that number is essentially the Jones polynomial. Yeah. And this is a kind of a, that's what's cool, right? You have infinitely many of them. Just choose your favorite Lie algebra, choose your favorite representation. It's a composition of maps, so it's a composition of matrices. Whatever you get is a non-invariant. Yeah. So the quantum groups give us the corresponding matrices. I'm not going to explain what quantum groups are. I'm not going to explain it. And why are these called quantum invariants? That's a good question, because they come from quantum groups. Why are quantum groups called quantum groups? Let's just use it as a black box anyway. There are also categorifications, right? If you have heard about Hovanov homology, they find in a very similar way. The problem is all of them behave similarly. But it looks from the outset, and this is where my brain went wrong, like there's something really cool going on. You have infinitely many invariants. So there should be something good among them, right? So you have infinitely many of them. The example, just to keep in mind for the Jones polynomial itself, you take SL2, the easiest non-trivial Lie algebra, and you take the easiest non-trivial representation of it. It's defining two-dimensional representation. And the R matrix is then a 4x4 matrix. Yeah? 2 times 2, that's why you have 4. And it looks like that. Fine. The only thing you need to know is if you specialize Q to 1, this is just a swap matrix, because this little term here, that was too much. This little term here just dies, right? This just will be 0, no? And it's just a swap. It's kind of a quantization of a swap matrix. So this R here, the crossing, is a quantization of a swap matrix where you can now distinguish over and under. Yeah? It's a swap, right? It looks like a crossing. And it's literally just a quantization of a crossing. Right? So here is our friend Jones, and kind of there are some more examples. Whatever Jones is, what I just showed you. The color Jones would be for a higher dimensional representation of SL2. You could do something like SL3, and it's defining representation. There are homology versions, like Hovanov homology, and there's a celebrated Alexander polynomial, which arises from a Lie superalgebra. Don't worry too much about it if you don't know what a Lie superalgebra is. But anyway, so this is kind of a whole zoo of these invariants. And what I wanted to do is the following. I wanted to run them on the set of knots, essentially. It's kind of a lot of fun. So the set of knots is really large. So here, if you don't know what a prime knot is, it's like a prime number. Don't worry about them. It's like there is a list of those knots, and they determine all other knots. Fine. And you can just list them by the number of crossings, the minimal number of crossings they have. And as you can see, this grows exponentially, because what you see here is actually a log plot. So it's 10, right? This is a log plot. There's a log scale here. So here's 10, 1,000, and then 10 to the 5, 10 to the 7, 10 to the 9. And such a line in a log plot is exponential growth. So the number grows exponentially. So there could be a lot of data you can analyze. You can just run your Jones polynomial or whatever over this set of data, right? You could just do that. And that's essentially what I did, or what we did. Okay, and then just want to make sure, and then we're going to play around a little bit. So, oops, I need to zoom out a little bit. Okay, so you can ask the naive question. Yeah, so how good is homology? I just told you usually see homology on easy spaces. That's why you get the impression it's actually pretty insanely good. And yeah, you usually see those quantum invariants of Jones polynomial and friends on easy knots. So you get the impression they're extremely good. Like here, Kronheimer and Morfka gave a really beautiful ICM talk. If you just Google that one, you will find it. And it's very, very nice to watch. It's excellently great. Beautiful, and they talk about one of these Jones polynomial is really good type things, namely they detect the unknot, right? In contrast to homology, which does not detect the sphere, at least the Jones polynomial, or more formally Hovanov homology, detects the unknot. No? That's not a bad start, but it's exactly what I think as like the orange and donut problem. The unknot is a really easy knot. It's not bad that it detects the unknot. It could be much worse. But yeah, so what about general knots, right? So let's say we put all knots in the back and grab out one randomly. How likely can, well, let's say the Jones polynomial or Hovanov homology, or whatever you like, distinguish them from all others? This is this detection property. So what is this ratio about different values it takes over all possible values? What is that ratio? Where does it go? Yeah, and turns out that the ratio is not all that great. But anyway, small number coincidences. So a lot of work for a lot of people have been around those. Yeah, it sounds a bit unfair if I call them small number coincidences, but in some sense they are small number coincidences. So Hovanov homology detects a lot of. So building on the work of Kronheimer and Morfka, they have a proof that actually generalizes to certain types of other knots. And yeah, what do you see here? It detects the trefoils or the unlink or something, right? This is exactly my, nowadays I understand, this is exactly my orange and donut type thing. Because in reality, they are really, really bad. So I show you something fun. So this is joint work. Ooh, top stories. No, I don't care. This is joint work with Victor Zhang. And Victor has set up a really beautiful website here. So, Dustbringer, oh, very good. The knot comparison website. We can zoom in a little bit. Ooh, beautiful. And we can just click here and see the various stats. Let me just go to Jones polynomial. Right, so here's Jones. And we can see here that the Jones polynomial at 18 crossing knots, it is at 41.6%. So it only detects 41.6% of 18 crossing knots. that is not very great. And you can literally see how it will drop down to 0 eventually. Here's a one-off homology. It's a bit better. It's at 50%, let's say. But not all that much better. Yeah, the Alexander polynomial is like really, really bad. It's 11%. And whatever, you can, put in some of the others and they all satisfy the same type of problem, which is like very sad. So this website is beautiful. You can play around with it a little bit. You will see those beautiful pictures. Excellent. I will come back to them in a second, but I really recommend, here is the link. I really recommend to play around with that website. So the problem is they all fail to detect knots, and you can even prove that. So I recently came up with a way to prove that, and it's not a difficult proof. So essentially what you can prove is they all decay to 0 eventually, and not even eventually, but actually exponentially fast. Yeah? And it's essentially, I can't prove it for all of them, but it's essentially true for all of them, which is like very, very sad, right? It's like homology. Homology is not a good invariant. These things are just not good invariants. That's just what it is. It's just what it is, right? It's exactly the same story. So here it's exactly the same. There's this bias or no small things, but eventually they all just die off. And you can literally explore on this website why this is the case. For example, let's do our friend Jones here. Let's zoom out a little bit. So no, Jones is a bit too far away. Let's use Hovanov. Why not? Okay. So here is the plot of all roots of Hovanov polynomials. And what happens is the following. So you see this type of picture, which is already a bit curious. Right? So it's kind of a biased. It's a biased. I take all Hovanov polynomials for, I think this is 16 crossing, not data. Yeah. Take all of them together and plot all their roots. Here, this green thing is a unit circle. Yeah. And you can already see this is kind of a strange and biased distribution of the roots. And that's why it's so bad, right? It's like almost all roots are at the same spot. And you can literally see that if I turn on the heat plot. So here, my axis, I can zoom in a little bit for you. Here, my axis just goes between no root or some root. So that's why it's just, essentially this should be white, right? So this is black and white. It's blue, it looks a little bit better. But anyway, black and white. So, but the problem is, if I turn on the brightness, so I make this scale a little bit different, I factor in the multiplicity, you will actually see what happens. And you will see why the knot detection is so bad, because almost all polynomials are the same in a certain sense. So if I factor in the heat, right, here's the multiplicity now. So it looks like it's called a heat plot. You'll see why it's called a heat plot. It's very fiery, right? So let's zoom out a little bit. So if you factor in the heat, you'll see that actually, right, it eventually just concentrates. Oh, this is fantastic. So Victor has done a really great job. This is fantastic. It actually just concentrates in very, very few spots, which is literally saying the polynomials are almost the same for almost all knots. So this is the picture eventually. So almost all roots are at those little spots here, right? So it's kind of this is what happens for all of them. Here's Jones. Jones is a little bit far zoomed out. Let me zoom. Can I zoom in here? Well, let's use one of the others maybe. Now it died. Now it died on me. Too bad. Let's reload it. For example, this one here, and you can see the same pattern. Almost all roots are at the same spot if you count in multiplicities. But yeah, exactly. So really beautiful. Oh, beautiful. I could play around with this all day. And there's a lot of more data that you can explore yourself, which kind of explains why all of these invariants are, let's just say, not all that great. Yeah, I have some more material here. The slides are all online. But essentially, that's all I wanted to say. So kind of the point here is these quantum invariants are sadly not all that great, and you can even prove that they are not all that great, which is an even stronger statement. So it's more than just an analysis of the data. You can actually literally prove that they are not all that great. Too bad, too bad. And I've studied them for a quarter of a century now. Yeah, and I don't know how I feel about it. Anyway, I hope you enjoyed this video, and I also hope to see you next time.